Good afternoon, everyone. Thank you for being here. My name is Hen Yu, a PhD student from the Chinese University of Hong Kong. Today, it is my pleasure to present our work, Hierarchical Graph Information Bottleneck for the Multi-Behavior Recommendation. This work was done in cooperation with Tencent Group and the Fuzhou University. So, what exactly is the multi-behavior recommendation? In most online platforms, users engage through multi-types of interaction behaviors with the platform. The goal of the multi-behavior recommendation is to effectively leverage the various auxiliary behavior like viewing, carting to enhance the prediction performance for a target behavior, which is often the sparse part of the primary interest, such as purchase. As you can see in the right, the SOTA approach typically adopts a hierarchical design, which can be divided into two main approach. The first, the cascading approach, which models the natural cascading sequence of the behavior. For instance, the users view first and then cart and then buy. And the second, the parallel paradigms. Since the cascading relationship aren't always strict, and this paradigm using the parallel encoders to design the modules to uncover the inter-behavior relationships among the behavior. However, existing approach still facing the two key challenges. First, there are several distribution disparity across behavior. As the histogram on the bottom shows, the behaviors like viewing are substantially more frequent than the target behavior like buy. And so this imbalance can lead to the popularity bias from the dominant signal and increasing the risk of the overfitting on the sparse target data. And the second major challenge is to negative transfer from the noise behavior. The many auxiliary behavior are implicit feedback and don't directly reflect the user true interest. So this noise can negatively impact the target behavior prediction, leading to a phenomenon known as negative transfer. So to check these challenges, we propose the HGIB framework. The core idea is to integrate the information bottleneck principle into the hierarchical model design. And for those unfamiliar, the information bottleneck principle is information theoretical framework to learn a robust representation. The goal is to learn a compact yet sufficient representation of the input X and preserve the quantitative information relevant to the target Y and will eliminate the task in relative redundance and noise. And our framework has two components to achieve this. Information theoretical objective that guide the representation learning, and a graph refinement encoder, which explicitly remove the noisy interaction from the data. Okay, let's now dive into the details. We apply an information bottleneck principle to each layer of the hierarchical model. The objective function as is shown here, and the first term is the preservation part, to pushing the learned representation to preserve the task-relative information about the final target behavior. And the second term is the compression part, which we discard the in-relative information, and it push the current layer representation to discarding the information from the previous layer that are not useful. Of course, directly optimizing the mutual information is intractable. So we should do some suitable approximation. First, to maximize relevance term, we derive into the tractable lower bound. As the equation shows, the natural composed into the three parts. Thus, it equivalent to the following training objective: standard recommendation loss, preservation loss that we implement use contrastive learning and regularization term. And next, to handle the compression term, we use in HSIC practical and effective approximation. It allows us to measure and minimize the dependency between the representation from the different behaviors layers. And finally, to explicit removing the noising, we introduce the graph refinement encoder and do it from the noise interaction from the data and to further reduce the negative transfer phenomenon. Here is what our framework looks like. We instantial with a parallel backbone. As you can see in the figure, the model has a hierarchical structure starting from the unified encoder and then branching into the behavior-specific and behavior component encoders. At each step, we apply our preservation loss and the compression loss to do the information bottleneck. And as you can see, each encoder is a graph refinement encoder, which denotes the interaction graphs before the performing the message passing. Now, we conduct the extensive experiment on the 3 public datasets. And according to the experiment result, we have the following observation. The multi-behavior recommendation, multi-behavior methods with hierarchical design constantly overperforming than the other methods. And moreover, HGIB achieving the best performance across all the datasets, demonstrating its effectiveness. And to demonstrate our framework potential for industry application, we evaluate it into 2 large-scale industry datasets from the WeChat platform for the news and live streaming recommendation. As a result shows, HGIB achieving a significant improvement over the SOTA baseline Mueller. We saw a nearly 50% relative improvement in the hit rate for the news recommendation and over 5% on the live streaming. And the result shows our method can effectively leverage rich and diverse multi-behavior data for a large-scale recommendation. And what's more, we conduct a 15 days online A/B test in the WeChat platform for the news recommendation service, and serving over 20 million users, and HGIB achieving a significantly improvement in the hit rate, click-through rate, and the social sharing rate over the SOTA baseline. And the source code have been made available at the provide GitHub link. And thank you for your attention. Thank you.
How do you balance removing noisy signals with the risk of throwing away rare but highly predictive behavior patterns? How do you tune the trade-off parameter beta in practice? And how sensitive are your results to this choice?
Actually, it depends. The different data set, maybe we have different results. As you can see, we use 3 data sets. Taobao and Tianmao is similar, and the Jingdong is a little different because the Jingdong have a very high transfer rate. A lot of users who viewing the items in the Jingdong, and then their view interaction will be maybe 30%, over 30% user, their view index will be transferred to a by index. Maybe the dataset is processed by a lot of filtering, so the dataset seems different. So the question is, it depends. Okay, depends to the actual platform and the datasets.